Okay, so this goes along with torque, and if I can do this right. So we have same quarter, or 2 quarters on each end. Both of them supposed to have like same kind of weight to them, right? So if they have the same mass, or same weight, the amount of torque that they're producing should be equal to one another, right? Now, since they're at the opposite ends, and if I can balance this, no. Here, I'll just find that equilibrium point. You want to try?
Me?
You.
I'll try it.
All right, try it.
Might as well. It looks pretty difficult though.
Because you want them on the same end.
I feel like I need to put on the flat part too.
That's what I was trying to do as well. Okay.
So,
All
I was
right.
like, don't move, don't move.
So hopefully you got to see that on the camera. If not, he did get it for a little bit. All right. So if we had the torque of one coin, the first coin, it's supposed to equal to the torque of the second coin, and if they're at the same mass, the torque should be the same. If we found the distance of the full pencil and everything, since the mass is supposed to be the same, right in the center of the pencil, that's where we should have equilibrium balance at. So torque of 1 minus torque of 2 should equal to 0 in that situation. And if we want to kind of so if they were both equal, we subtracted the 2, our net torque would be 0. Now, if we kind of take this application up a little bit higher, so a little bit bigger standard. We have a nice childhood memories. We have the seesaw. Okay? Now,
I thought it was some Xbox or something.
no. Okay, no. Seesaw, the fulcrum is right in the middle no matter what, right? It's like they measure out the board, half the board, that's where they put the axis of rotation at. Now, seesaw, usually we had 2 people on it. One kid on one end, the other kid on the other end. And if both kids were close to the same mass, you can honestly try to get that balanced out, right? A lot of times when, if you're at camp or something like that and you're on the teeter-totter, trying to find this kid that had about the same mass as you was kind of difficult. So more than likely, one kid, let's just say, was at 30 kilos for a mass. That's roughly about 62 pounds. Then the other kid is at 55 kilos. That's over 100 pounds. Now, if we have this difference in mass, what usually happens?
One guy's gonna get to the ground, one guy's in there.
Yeah, one guy goes to the ground, the other guy's. So this guy, the heavier one, is going to be going down, the other one is up in the air and stuck there until said person either pushed off or got off, right? Now, what we could possibly do is figure out where that fulcrum needs to be at so that they are equally balanced. Okay? So let's kind of look at that today for our first problem. Okay, so Carrie Ann she's at 56 kilos, and Aaron is at 43 kilos. They want to balance on a 1.75 meter seesaw. Where should the pivot point be at? So I'm going to move that over there so we have fresh board over here to work on. All right, so the one thing that they both have in common is they both have the acceleration due to gravity acting upon them, right? So we can figure out the force for each one of those. All right, so force of Carrie Ann, 56 kilos times 9.8 meters per second squared. Force of Aaron, 43 kilos times 9.8 meters per second squared. So if we look at this one, 56 times 9.8. Coming up with, it's 548.8, so I'm just going to round up to a whole number, 549 newtons for Aaron, 43 times 9.8. Or 21 newtons. All right, now for the next part, for our lever arm, our radius. Which one do you want to work with? You want to work with Carrie Ann or Aaron?
Carrie Ann.
Carrie Ann?
Yep.
Okay. All right, so the radius for Carrie Ann would be 1.75 meters, because that's the full length of the seesaw board, minus whatever the radius of Aaron would be, right? And if we're talking about net torque, you know, like I said, for them to be equal to one another, figure out the R. So F of K, now we said that the RK that'd be true, that if we subtract the two, they would be equal to 0, so F of K times 1.75 meters minus RE minus F of B to 0. So what we're gonna need to do in this first part is figure out what is the radius of Aaron. Okay? So let's kind of put in our numbers that we have over here. F of K, 549 newtons times 1.75 meters minus R of E minus F of E, 421 newtons times R of E, and that is equal to 0. So as we keep on going and everything, you know, we're gonna take 549 times our 1.75 minus R of E, so 549 times 1.75. I'm gonna just say that it comes out to be 960.75, so 961 meters minus 549 is RV minus 421 newtons, R of E is equal to 0. So going through this whole thing, I'm coming up with for the radius of Aaron will be at 0.99 meters. Now to find the radius of Carrie Ann, we're going to take 1.75 minus 0.99 meters. And we come up with 0.76 meters. So if we're looking at, you know, relative for Carrie Ann, move the pivot point 0.76 meters from the end of where that she's at, or if we're looking at Aaron's perspective, we move it 0.99 meters, and that's where the pivot point should be at, and that's where they should be able to balance the seesaw.
So if you find the center, 1.75 divided by 2, so it's 0.875. So for Aaron, you have to say move towards Karen, point, 0.12, like
Right.
12 basically.
Yeah, yeah.
So you just shift it. Is that what you're saying?
Yeah, because this is going from the very end where she's at.
Yeah. So if the middle's rounded to 0.88, you just shift it like 0.11 over, or
Yeah.
but you shift it opposite of the person, right?
You shift it,
Well, I guess Aaron's you would shift opposite because she's the lighter,
correct.
but then Karen's either way it's shifting towards Karen, basically, right? Because
Yeah.
she's the heavier one.
Correct,
Okay.
correct. Okay? Questions? Any kind of questions? All right, I think we'll just stop there for today.